Hey guys, here we're talking about projectile motion, section 3.5 out of your book. And projectile motion is a special case of free fall in that the object in projectile motion is only under the influence of gravity. And if you remember, that was how we defined an object in free fall. So let's take a look at one of the very first things we looked at when we were talking about an object in free fall. So let's look at a ball dropped. So here we have the ball in its initial position. So we're going to say at t is equal to 0 seconds. And we also knew that the initial velocity of the ball, I'm going to say v naught in the y direction, is 0 meters per second. And then as the time progressed, the ball starts to fall. So we have here at time equals 1 second. And the velocity of the ball is now around, we're using some rough estimates here, but about 10 meters per second, because we know that gravity accelerates things in a downward direction. AY is 9.8 meters per second squared. We're using 10 just for the ease of calculations here. But after 1 second, it is now 10 meters per second. As the ball continues to fall, let me draw my velocity vectors here. That's my velocity vector there. Here, my velocity vector is a little bit bigger. At t is equal to 2 seconds. Velocity in the y direction is now negative 20 meters per second. T is equal to 3 seconds. Velocity in the y direction should be negative 30, and so on and so forth. Zoom out a little bit, and then at 4 seconds, velocity in the y direction is 40 meters per second. Pointed in the down direction, we know that the time is the same for each one, but notice the distance between each one is increasing and the velocity vector is also increasing in down direction because it's accelerating. Okay, we figured that out. Now what we're going to do is we're going to now look at a ball rolled off a table. So one of the things we're assuming in this case is now, since the ball is being rolled off of the table, it has some type of initial velocity in the x direction. Now what happens is the ball continues to be accelerated in the y direction, but in the y direction only. So at second equals 1, I'm going to kind of draw these little dotted lines over here, that about this point is where time equals 1 second is. Notice the y direction should still remain the same. Gravity still affects it, so it should still increase in velocity in the y direction. But once again, we said that it's only under the influence of gravity. Gravity affects things only in the vertical direction, which means this initial velocity in the x direction remains unchanged. At second 2, I have velocity going down in the y direction, increasing at the same rate. But once again, my velocity in the x direction remains unchanged. At t equals 3 seconds, my velocity in the y direction remains unchanged, and my velocity is increasing as it should in the y direction. Now notice, as it progresses through time, as it's falling, it's increasing distance in the x direction, but at a linear rate. Once again, it is not accelerated in the y direction, therefore it is constant in the x direction. So over here, I understand that. So once again, velocity is constant in the x direction, so no acceleration occurs. So my blue vectors, what I'm drawing here, they should remain the same value throughout. As my ball continues to fall, over here at 4 seconds, he's way over here, which has my velocity vector going down here, and once again, my velocity vector remaining unchanged in the x direction. So a few more things to talk about here. Object is accelerated by gravity only, so the y direction velocity changes. Another thing that's actually very interesting, it's something Galileo pointed out several hundred years ago, is that a dropped ball will hit the ground at the same time as an object projected horizontally. And once again, projected simply means thrown that way. So that's just projected means. It means thrown at a direction. So projected horizontally means rolled horizontally off the table like this ball is doing. So we have a lot of information here about this ball being dropped and being rolled off of the table horizontally. One of the things that is really interesting about this is all of the kinematic equations are valid. So one of the things that will be most useful to us is understanding the fact that only acceleration in the y direction happens. So what that means is a couple things. One, in the x direction, there is no acceleration, so the x direction velocity is the x direction velocity. The only thing I can use in terms of the time is here, the distance or displacement in the x is velocity in the x times time. So I'm gonna put a little dot over time just to know that, like our riverboat questions, time happens for both the x and the y component simultaneously. So the time, when an object is falling, the time in the air is the hang time. Over here, so we can kind of see over here that as it travels in a horizontal distance this way, it takes the same amount of time for it to fall going down that way. So once again, time happens for both components at the same rate. The other thing that we have to think about is all of the kinematic equations are valid. So all that means is we have the first equation that sounded like VF equals V naught plus AT. Well, the way we would look at it this way is VFY equals V naught Y plus AYT. That simply means in the y direction, final velocity in the y direction is equal to the initial velocity in the y direction plus acceleration in the y direction times time. Once again, all of that just to say acceleration in the y is going to be negative 9.8 meters per second squared. Not too tricky. All of the other equations sound the same. We have the second kinematic plus C2 AY dy. So we're looking at displacements, remember? So displacements is going to be important to us. And then the third kinematic, displacement in the y direction, V naught y time plus 1/2 AYT squared. All these equations handle exactly the same thing. One final note as we're looking at this diagram. The main difference between a ball being dropped and a ball being rolled off the table is the velocity of the object. As the ball is being dropped, notice it only keeps increasing in the y direction. Well, that makes sense. It's only being accelerated in the y direction and nothing is occurring in the x direction. But as a ball is being rolled off of the table, something a little different happens. At this t equal 1 second or 0 seconds, we understand that yes, it has an initial velocity in the x direction. It's being rolled or projected off of the table. But in the y direction, it's still being accelerated. At t equals 0 seconds, nothing is happening. It's just staying at rest in the y direction, but it does have speed in the x direction. In the first second, this t is equal to 1 second here. Notice, I'm going to draw my parallelogram here. I draw this vector, but this is now the resultant velocity of this due to both the y direction velocity and the x direction velocity. As time progresses, we see a change in this resultant velocity vector. A couple of things should happen. It's kind of hard to tell as we sketch it out here. But what should happen is the resultant does get longer and it starts pointing in the downward direction. So kind of leaving this cool tidbit up for you guys to figure out, but why does the velocity in the y direction, why does the resultant seems like it starts pointing more and more in the y direction? That's kind of cool. Once again, notice that all of these blue horizontal vectors, we're trying to illustrate the fact that they remain the same, the y direction changes. So we have this interesting velocity thing as it starts pointing more into the down direction. That's cool. One of the questions that we'll end up asking is how fast, or what is the velocity that the object hits the ground? It's tempting to say 0 because it hits the ground, it stops moving, but remember, we're assuming that it's hitting the ground at a certain speed, at a certain angle. When it asks those kinds of questions, what we're doing is we are looking for the angle of the resultant velocity with the ground. So as it hits the ground, so we'll say hits the ground, we're looking for the magnitude of the resultant vector, so Pythagorean theorem between the velocity in the y direction, this guy here, and the velocity in the x direction. And we want to know what that angle is. And typically, I like using that inverse tangent of the y direction over the x direction. That's generally how we solve those. Those are pretty straightforward. Okay, so we are now going to talk about how to do one of these. I'm going to call these a type 1 projectile, something projected horizontally from an elevated surface or a ball being kicked off a cliff. Okay, so this is one of the first examples in your book, but I like calling it this way. So once again, a type 1 projectile is an object projected horizontally. What this one is a car driving off a cliff. It's like a stunt car or something. And we want to make sure it lands 90 meters from the base of this particular cliff. This particular cliff, we know, is 50 meters tall. And so before we kind of start playing with any of the math, let's understand what the givens are. We know that the velocity in the y direction is 0 meters per second. This car is being given some type of initial velocity in the x direction. I just don't know what it is. So v naught x is, I don't know. I do know that displacement in the x direction is a positive 90 meters. I know a displacement in the y direction is actually a negative 50 meters. The object is landing below its original starting point. And once again, I know acceleration in the y direction is negative 9.80 meters per second squared. So this car is going to land somewhere over here. That's where we expect the car to land. So the first question is, how fast does the car have to go? In other words, what is the initial velocity in the x direction? So kind of bear with me through the problem solving process here. Distance in the x is velocity in the x times time. Well, kind of go through our quick check here. I do know what the horizontal velocity or distance is, but I don't know the horizontal velocity and I don't know the time, so I get stuck. But once again, we have to remember that the time to fall is the same as the time to travel horizontally. So a quick check, and since we are all kinematic experts at this point, I'm going to use the third kinematic. Displacement in the y is v naught in the y times time plus 1/2 ay t squared. Solving the algebra tells me it's t is equal to 2 dy over ay. Understanding this, once again, this velocity in the y direction drops out to 0. So I'm going to plug my numbers in here, make it look like this. negative 9.80 t squared. So when I crunch that number, I get about 3.19 seconds for the object to hit the ground. Since I know that's how long it takes to hit the ground, distance in the x is velocity in the x times time. That time value goes into that guy right there. I know the 90 meters. Looking for my time value, which is now 3.19. So I get this car had to have been traveling at least, or exactly 28.2 meters per second to hit the base of the cliff, or hit 90 meters from the base of the cliff. A second question that you're probably going to get asked is, what is the velocity of the car at the impact, or what is the angle of impact of the car? And so what we're doing is we're kind of zooming in on this ending part here. And once again, we're looking at the velocity vectors. That's going to give us the angle of how this works. The velocity vector, once again, remains unchanged. We know that it now has some type of final velocity in the y direction. When it asks us that angle question, we're looking at the resultant vector here, and typically that's the angle. That's the angle of impact at the floor, the angle of impact with the ground, something like that. So knowing this information, we can figure out how fast it's moving in the y direction, or the velocity in the y direction, using the second kinematic. So let's write our question here. Velocity of car at impact. I need to know how fast it's moving in the y direction. So VF y squared equals V naught y squared plus 2 AY dy. Plugging in what I know, once again, there's nothing in the y direction. VF y squared equals 2. The gravity is negative 9.8. The displacement here was negative 50. Notice these two signs here are going to make the radical work in that case right there. So the final velocity in the y direction ends up being 31.3 meters per second, but it's in the down direction, so I'm going to put that negative here. Remember, when we take the square root of all that, we have to make sure we have the plus and minus. Okay, so we have to make sure we understand which way that's pointing. It's going down. So our good friend Pythagoras lets us know that the resultant speed, or the resultant velocity of this, is going to be 28.2 squared plus 31.3 squared. That's the x and the y direction. Here the resultant ends up being 42.1 meters per second. So that is this guy right here, 42.1 meters per second. And then the angle of impact, once again, the car is hitting the ground at that particular angle. We like to say this is the inverse tangent of that y velocity there, so 31.3. The x direction remains unchanged, 28.2. So we get the angle of impact is about 47.9 degrees. And the way we phrase this, we'll say it to the ground. All right, so there is a quick overview. This is our first go at these kind of projectile motion questions. We're calling this type 1 projectile. They're not really called that, but I like breaking up this way. They all kind of end up doing the same thing anyway. But a type 1 projectile is a horizontally projected projectile. Basically, think about a car being, or a soccer ball being kicked off of the cliff. It only has an initial velocity, 0 velocity in the y direction, increases on the way down. The hang time is the same as the horizontal travel time is the same as the vertical hang time. So the time is the thing that's going to be what connects these kinds of questions and how to do them. All right, so we have our problem set, just a handful of questions. Make sure you understand how to do those, and I will see you guys later. Thanks. Bye.